So far in section 9.1, we've had a lot of setup. We're setting up for you a lot of basic theory about confidence intervals, what the point estimate is, what the margin of error is, how confidence intervals work in general theory in terms of how they're created, what the width of the interval is related to the error, what the confidence level is, what alpha is, etc. Lots and lots of theory, but what we haven't done really is create these intervals that we came up with here to know where the numbers came from, right? We were given numbers and we created intervals, but where did the numbers come from in the first place? That's the part we haven't done yet. And that's about to change right now. So we have here the formula for the confidence interval for a population proportion. This is p hat plus or minus z alpha over 2 times the square root of p hat times 1 minus p hat over n. Now this formula is not needed to be memorized, nor do you need to put it on your note sheet, because remember, for the final exam and for exam 3, if you're in a face-to-face class, you're allowed to use this entire inferential statistics info sheet, which is in your course pack. It's in neon green in the most recent course pack. And you can see right here in the top left corner, I have this formula, p hat plus or minus z alpha over 2 square root p hat times 1 minus p hat over n. I even tell you what section you learned it in, which is section 9.1. And you can see you're going to know a whole bunch more confidence intervals by the time chapter 11 is done. All right, so if I were you, I would take out this inferential statistics sheet right now, staple them all together, put your name on them. You get to use them on your exams. Okay, so let me go back to the notes. Now, what does it take to make this interval? There's some requirements. First thing you have to do is you have to know a point estimate, which is p hat. And don't forget that p hat is equal to x over n. We learned that in section 8.2, right? All right, so p hat is x over n. Of course, as in most things with this course, we cannot do anything unless we know it's a simple random sample. If it's not a simple random sample, you're not doing it, right? Then we need to know that n times p hat times 1 minus p hat is greater than or equal to 10. We learned that in section 8.1. It's to ensure that the distribution is normally distributed. We learned that in section 8.1, or 8.2, excuse me. Right? Then we also learned in 8.2 that we need the sample size to be less than 5% of the population size. And that's to ensure that the distribution is independent, or the samples, excuse me, samples are independent. Now that thing that we're adding on and subtracting away in the back end, that z alpha over 2 square root p hat 1 minus p hat over n, all of that is called the margin of error. That's the formula for it. But also remember that it's half the width of your interval. Now sometimes the fact that it's half the width of the interval is way more useful than the actual formula itself. So sometimes we will use the formula, sometimes we'll use that it's half the width, whichever is more convenient for us. And we'll run into this in a little bit. But first, let's figure out what the z stuff is. So z alpha over 2 is called the critical z value. And remember in section 7.2, we learned that alpha over 2 is the area in the right tail, because that is what we learned for a notation, right? We have a z with a little subscript after it. It means that alpha over 2 is the area in the right tail. And we found these using inverse norm with the left tail probability. And of course, since it's a z-score, that's the standard normal distribution, which means that the mean is 0 and the standard deviation is, of course, 1. We also learned that in chapter 7. All right, so we're going to use these ideas to find some particular critical z values. So I'm going to set up here, we have 90%, 95%, and 99%. Let's start off with finding alpha. Alpha is the complement of our confidence level, right? So since our confidence level is 90%, alpha would be 10%, which is 0.10. All right, so there's our alpha, 0.10. All right, so what does that mean for the area in each tail? Each tail then has alpha over 2. So alpha over 2 would be 0.10 over 2, which would be 0.05. So now that leads us to having to find this. lovely critical z-values. So let me draw a picture real quick of what's going on. There we go, I got a picture now. So you can see you have the 90% confidence in the center. Oops, I didn't put that in there, but let me shove that in there just so you can see. So the middle part is 90%, and that means that each of the tails is 0.05, right? So the center is 0.9, and then each of the tails is 0.05. There we go. And each of those is alpha over 2. Right? So what you're looking for is these two z-scores. Well, you're really only looking for one of them, because if you know one, you know the other, because the graph is symmetric and 0's in the center. So now how do we find the z-score from a given area? Well, we use inverse norm, right? So inverse norm, 0. Now you have a choice here. 9.5 will get you the one on the right, 0.5 will get you the one on the left. It doesn't really matter that much which one you pick, because they're the same number. It's just one's negative and one's positive. Let me prove it to you. So I go to distribution, pick number 3, inverse norm, 0.95, 0, and 1. There we go. And then if I do it again, distribution, number 3, I pick 0.05. There we have the negative one. And when they're looking for the critical value, they're really looking for the positive one. They're looking for positive 1.645. So that'd be equal to, well, approximately. It's of course being rounded, 1.645. That'll be your z alpha over 2. And there we have it. Now, to do this problem on your exam, you would have to do exactly what I've done here. You'll have to draw a picture. You'll have to shade it. You'll have to show your calculator entry. That's the inverse norm part. And again, you can use either 0.95 or 0.05, but you definitely want the positive number over here. So you're looking for z 0.05. Z 0.05, that's the area in the right tail, is 1.645. Oops, approximately. And then we're just going to do it again and again for the other two. All right, so if we have 95%, then our alpha is 5%, which would be 0.05. That means that alpha over 2 would be 0.05 over 2, which would be 0.025. So I'm going to do the same picture, but alpha is going to be 0.025. 1 second. There we go. I drew all of them at the same time just to get it done. All right, so the middle is 95. The tails are 0.025, right? And then what we're going to have to do is we're going to have to do inverse norm, but we can have a choice. You can either do 0.025, because that's the area in the tail, or you can put the center and the other tail together, and that would be 0.975, right? 0.025 plus 0.95 makes 0.975. So let me grab my calculator, say inverse norm, 0.975, that's 95 plus 0.025, and go down to paste and press enter, and I'll get 1.960 when you round it. So 975, that was 1.960. All right, so that would be z 0.025, 0.025 being the area in the right tail. So the area in the right tail is 0.025, that's 1.960. Remember that the calculator always takes left tail area, so that's why I have to put 0.975 here. But the picture is actually 0.025 right here. It's the area in the right tail for the subscript, if you will. And if you like, you can say this one's 0.05 right here. So 0.05 and 0.95 add up to 1. 0.025 and 0.975 add up to 1. Then we're going to do it again over here. This is going to be 0.01 because it's going to be 0.99. Oops, it's sorry, 0.005. There, like that. That's 0.995, like that. Okay, so let me find that. So inverse norm, number 3, 0.995, go down to paste and press enter, and I get 2.576. And that would be the value there for z sub 0.005. So 0.005 is 2.576. So it's the same process over and over. You will definitely have to do one of these at least on the exam. So be prepared. There will be one in there that you'll have to do by hand like this. These three, once you know them, you now know them forevermore. You don't ever have to find them again unless I ask you to find them again showing all work. But if you're not asked to find them showing work, then you can just know them. Right? And I'll give you a hint, you don't actually have to put them on your note sheet. That's because you're going to learn something in 9.2 that means that you'll be able to find these quickly and easily. But wait on that for section 9.2. So for right now, this is how to find them by hand, and you will definitely have to find at least one by hand showing your graph and everything labeled appropriately, just like I have labeled here, and then your calculator entry and so on. Keep in mind that these pictures don't have anything in them that you shouldn't be drawing. So there's nothing in there that is extraneous. You need to draw pictures that look just like that and almost as pretty as that. Notice, by the way, that for 0.9, the number is 1.645, meaning that area in the center is only 90%. For 99%, you can see they're drawn to the same scale. You can see how big that area in the center is and how little bitty the tails are. That's because the area in the tail there is 0.005, whereas the area in the tail over here on this left-hand one is 0.05. That's why the numbers are so vastly different for the inverse norm values, for the z values. All right, so now we know how to find critical z values by hand. Let's stop right there, and in the next video we're actually going to test our conditions for making the confidence interval, and then we're going to make the confidence interval using the calculator. I'll see you then.